This video is another in the series for Math 1224 for UTSA. Today we're talking about Chapter 7, Parametric Equations and Polar Coordinates. So 7.1 is about parametric equations. So we've got a quadratic function here. Y equals negative 1/4 times x minus 2 squared plus 4, or if we want in the general form, negative 1/4 x squared plus x plus 3. And I have a little sketch of the graph on the interval 0 to 6. So we're only considering x between 0 and 6 for this present example. So you've probably heard of parabolic motion. You throw something up in the air, it comes back down. It moves vertically and horizontally. Typically, we'll think of the horizontal as being time and the vertical as being height. But let's not do that. Let's think of the horizontal as being distance in the horizontal direction and the vertical as being distance in the vertical direction. So this is the path of the object through a plane. So it's going forward through space and then up and then down again. It's not turning midair. Like, assume there's no wind, but it goes up and it comes down and it travels horizontally a bit. Like if you throw a ball not straight up in the air, but forward a little bit, then it goes forward as it travels, right? And it hits the ground and bounces or whatever. So this can describe the motion of an object. So maybe there's some object, say here, and it's moving forward. And it's going to go through this parabolic arc until it hits the ground, right? How would we describe that as a function of time? The object moves. It starts out here, then it's here, then it's here, and so forth until it hits the ground. It moves through space. How do we describe that as a function of time? So I will look at an interactive graph here. So I've got the function put into Desmos. You can see the graph there. And there's the point that moves. As I increase the slider for t, the ball, say, goes from the starting point up to its apex and then down to the ground, right? And it's moving what's called unit speed. Notice that here in the formula for that point, this is an ordered pair. It's the x coordinate and then the y coordinate. Okay, so t is the horizontal, and then negative 1/4 t squared plus t plus 3. That's the vertical. Okay, so its horizontal speed is just like 1 unit per second. If I switch to this other point, notice that 2t is the horizontal, and then I've substituted 2t in t's place in the vertical. So as I increase this, it moves more quickly. What do I mean by that? Well, once we get to t equals 3, the ball is already at the ground. It moved, come on, it moved twice as fast. So in 3 seconds, it moves to the ground. So if I look at both together, the purple ball moves faster. It gets to the end in half the time, okay? If I include this, let's look at just this next one, where 3t is the horizontal, and I substitute 3t in for the vertical in that formula. This moves even faster. So once I get to t equals 2, it's already hit the ground. So if I back that up and look at all three together, I have 3 objects moving through the same path, but at different speeds, okay? So this is what a parametrization allows when you treat the variable not as x necessarily, but let's call it t for time maybe, but then the x coordinate is a function of time, and x could just be t as in the first case, x could be 2t, or x could be 3t, or x could be something else. In fact, let's do this. Let's duplicate this, change the color to, let's make it green, and let's do something a little odd. Let's make this, I don't know, e to the t power, okay? So I'll copy this, and I'll paste it in here. So e to the t is plugged into the function. So now if I back this up, it's not going to quite work. That's okay. That's okay. I think this will work. Okay. Sorry. That would work, just not the way I wanted, because the starting point would not be what I wanted. But that's okay. There we go. That should do it. Okay. So now if I move forward, see, the green one starts at a disadvantage. It's at the end of the pack, but then it quickly, does it win? The green one actually finishes first, because basically it's moving horizontally with exponentially growing speed. So it's slow initially, but then it surpasses the black dot. Okay, so the green dot wins even though it's slow at the beginning, and that's because I put in this exponential function for the x-coordinate. So parameterizations are really powerful. They allow you to describe a lot of variety in motion, not just the path, but how does the object move through the path. Okay, so let's get some definitions out of the way. So if x and y are continuous functions of t on some interval, then x equals x of t and y equals y of t are called parametric equations, and t is called the parameter. This is notation that you've probably seen before in Cal 1 at some, well, you've seen this notation in Cal 1 at some point, where the name of your function can be the same symbol as the variable involved. So y equals y of t. This right here is not y times t, this is y of t. In this context, y is the name of the function. But y equals y of t. In this context, y is the name of the variable. So it's serving a dual purpose here. And then this is just the same thing. X equals x of t. The x variable, the x coordinate, is some function of t, and that function has the name x. Okay. And as I said, t is called the parameter. It's no longer necessarily called the variable because we have lots of variables now. It is the independent variable. X and y depend on what t is, but in this case, t is called the parameter. The set of points x and y that are generated as t moves through the interval is called the graph of the parametric equation, and this is also sometimes called the plane curve. So what's next? Oh yeah, we're going to graph a couple of examples by hand. Of course, it's nice to have Desmos do it for us, but it's also good to see this by hand. So I've got something like a t table. We have three variables, though. We have t, x, and y. So I'm going to make up some t values and then see what x and y coordinates come from those t values. And we're using the interval 0 to 3. So I'll probably do 0, 1, 2, 3 as some basic examples. Maybe we'll do some fractions at some point. So I want to do, say, t could be 0, 1, 2, and 3. So when t is 0, what is x? So if I plug in 0, I get negative 1. What's y? Well, if I plug in 0, I get 2. So I'll have the order pair negative 1, comma 2. Negative 1, comma 2. And I can go ahead and mark out a point right there. Okay. When t is 1, well, if I plug in 1 here, I get 0. If I plug in 1 here, I get 3. So 0, comma 3. And I can go ahead and mark a point right there. How about 2? If I plug in 2, I get 3 for x, and I get 4 for y. So 3, comma 4. Well, if I plug in 3 for t, well, I'll get 8, comma 5. Oh, I forgot to mark that one. That's okay. So 3, comma 4 would go right here. And then 8, comma 5. I'm kind of eyeballing this a little bit, but roughly there. So I get something like the following. Oh, and also I should not go past 8 because we have a closed interval. It stops here. So that is the graph of those parametric equations, and it's a little janky there. Let's not worry about that. Okay, let's go look at the Desmos first. So there's the starting point, and I have these set up both to show the path and the object. So as this goes through, the path is there, and we get this. It looks like a bit of a parabola, basically. So if you look back at what I did by hand, yeah, that's pretty close, right? But of course, not perfect because it's by hand. Okay, what's next? I think another one of these. Yeah, graph the curve given by x equals 2 sine t, y equals cosine t, and t goes from 0 to 3 pi over 2. Okay, so let's say t will be 0 pi over 2. And maybe we'll do something like pi over 6 or pi over 4 at some point. Pi and 3 pi over 2. Okay, so if I put in 0 in for t, well, sine of 0 is 0, so x will be 0, and y will be 1. Cosine of 0 is 1, so 0, comma 1. 0, comma 1, so we're going to start out here at the top of what would be the unit circle, but I don't think we're going to get a unit circle here because of the 2. So what if I plug in pi over 2? Well, pi over 2, sine of pi over 2 is 1. 2 times 1 is 2, so x will be 2. And then cosine of pi over 2 is 0, so y will be 0. So you get 2 comma 0. Okay, so over here. So as time, in air quotes, goes from 0 to pi over 2, the object will move from here to here. So basically, we're getting motion like that. And if we were to do, say, pi over 4, we would get something here in between. Let's go ahead and do pi over 4. Okay. So if we put in pi over 4, well, sine of pi over 4 is root 2 over 2, so that'll be root 2. X will be root 2, or about 1.4. Cosine, well, it's going to be root 2 over 2. So I will get root 2 and root 2 over 2. Root 2, as like I said, is about 1.4, and root 2 over 2 is about 0.7. So 1.4 and 0.7, right about there. Okay, so we're going to end up getting something, well, that's way off, actually. So 1.4 and 0.7. Something like that. Hopefully that's closer. Something like that. Not drawing the best, but whatever. So let's go look at pi. If I put in pi, well, sine of pi is 0, cosine of pi is -1, so we get 0, -1. So that's going to be down here. So this continues down to here. Okay, it's a little wonky, but you get the idea. 3 pi over 2. Well, 3 pi over 2, sine of that will be negative. Sine of that is -1, so -2. And then cosine of that is 0. So -2, 0. Okay, so that's right there. So this continues. It looks like kind of a football shape. That's because I'm doing it by hand. I'm not very good at it. That part was pretty good, actually. So what we're getting is an ellipse. This is not complete because our interval ends at 3 pi over 2. If the interval ended at 2 pi, then this would connect, but it doesn't, so let's leave that off. Let's go look at a better version of this. Okay, so I've got the curve programmed in there. So as I increase capital T, I had to do that because of the way Desmos works. The capital T, it doesn't want to use lowercase t anyway. You can see the object moving, going around the ellipse part way, and then stopping at negative x equals -2, y equals 0 there, because the graph does not complete. The interval doesn't go all the way to 2 pi. Okay, what's next? All right, eliminating t. So what if instead of graphing by plotting, I wanted to turn this into something that's a little bit more recognizable and say, oh, well, can't I just write this as y equals f of x and then just graph it normally? How can I do that? So this is not always that difficult. It depends. Looking at this one, I want to solve for t and get x by itself. I'm sorry, get t by itself, rather. I want to get t equals some formula of x and then plug into here. Now, I do have to be careful when I'm doing this. I'll add 1 to both sides because I've got t squared, and if I try to use a square root function, I might run into a plus or minus issue. But notice that t is never negative, so that's okay. So here, this is the square root of x plus 1 equals t. Then I can plug that in for t. So y equals the square root of x plus 1 plus 2. So this is the closed form, what we're accustomed to, function that will have the same graph as this set of parametric equations. Of course, when you look at just the function like this, you don't have you have the path, but not the speed. How does the object move through that path? And we're missing that when we take y equals some function of x. Okay, let's do another one of those. That one was relatively easy. This one might be a little bit harder, and how you do it, it's up to you. It depends. So, oh, by the way, this is the same graph that we had earlier. So, one way to get started is to take this guy here and divide by 2 on both sides. So x over 2 equals sine of t. Now, I'm going to square both sides, and we're going to have to think back to pre-cal in order to basically complete this. This one, I'm going to take and square both sides as well. So y squared equals cosine squared of t. if I add these two together, sine squared t plus cosine squared t, I'll get 1, right? Pythagorean identity. And I can replace sine squared of t with x over 2 squared, which I guess I didn't need to do it that way, but I think it helps. And replace cosine with y squared. So this is the graph, or this is the equation, rather, for an ellipse. Okay, with major axis, well, 1, and then minor axis 1/2. That's like y squared over 1, or y over 1 squared, rather. So yeah, that's the rectangular form of the equation. So think of this as being something like a walking trail or a path somewhere, and you can walk on the path, you can jog on the path, you can go part way, stop, turn around, and then go back again. The graph here is just the path itself, but the parameterization, this is an individual path that might meander and go back and forth, or go quickly or slowly or whatever. Okay, what's next? Oh, parameterizing a curve. Awesome. So what if we have a path, a graph, and we want to come up with two different ways of traversing that graph? One way is to always say, oh, x equals t, that your x coordinate will just be whatever t is, and then y will just be, you just plug in t for x. This will be a parameterization, okay? And then for a second parameterization, you basically could do anything you want. X could be any function of t, so I could say, oh, x equals 2t, and then I just take this and plug it in for x. So this will be y equals 2t squared minus 2. That's another parameterization. I could do something like, well, there's different options depending on what section of the curve you care about. Because if I choose something like this, if I say, okay, uh, x equals, say, t squared, right? Then x will never be negative. Whereas here, x can be negative, but I can do that if I want. So then y equals t squared squared minus 2, which is, of course, t to the fourth minus 2. I could even do x equals, oops, I'm doing more than 2, I guess. I could do x equals e to the t, or 2 to the t, 2 to the t. And y equals 2 to the t squared minus 2. I could even do x equals, say, tangent of t, and y equals tangent squared of t minus 2. In fact, let's look at that one. Okay, let's switch over here. I've got the first one programmed in, and you can see that as I move the slider, the green dot moves around. Okay. And let's put that one away for a moment and pick up this one. This is tangent of t. So when t equals 0, we're there at the bottom as the other one started. And as we increase, this goes up pretty quickly. All right. If we look at, oops. If we look at both of them, this is complaining. I don't know why this is complaining. That's okay. That's fine. If we look at both of them, then when t equals 0, they're both at the bottom. As t increases, they both go up, but the blue dot moves much, much faster. That's basically because the tangent function is increasing the x coordinate more quickly than just saying t. Okay, let's get rid of those. We don't need those. So basically, plugging in the t parameter into the tangent function grows quickly because it's asymptotic. As t approaches pi over 2, tangent goes to infinity. So it goes up the curve very quickly. It moves very quickly. Okay, what's next? Okay, find two different parameterizations of x squared plus y minus 1 squared equals 4. So I recognize that this is a circle with center 0, negative 1 and radius equals 2. So what I'm going to do is I'm going to say, okay, this x, I'm going to call this 2 cosine t, okay? And this y minus 1, I'm going to call this 2 sine t, okay? So that I have x equals 2 cosine t, and y and y minus 1 equals 2 sine t. I didn't mention, you could say that x equals t. That would be fine, but it'd be overly complicated. We probably shouldn't do that one. We could, but it's just going to be harder than it needs to be. Okay, so rewriting this, I get x equals 2 cosine t, and then y equals 1 plus 2 sine t. Okay, so now I need a different parameterization. Well, what I can do is just swap the role of sine and cosine. That will work just fine. So let's do this. Let's say that this factor or term, this term, this is 2 sine t, and this one is 2 cosine t. Okay, so I'll get x equals 2 sine t, y minus 1 equals 2 cosine t, y minus 1 equals 2 cosine t. So rewriting this, I'll get x equals 2 sine t, and then y equals 1 plus 2 cosine t. And these might look very different. I've swapped sine and cosine, but they're both parameterizations of the same plane curve, so they'll make the same path, just in a different way. So let's take a look at that and see what that looks like. Okay, so I've got this first little folder. I have the first parameterization set up, and this second folder I have the second parameterization set up. So if I turn this one on, you can see we start at this point here at 2, 1. As I increase t, this carves out a path. That's a circular path with a center at 0, 1, and the radius 2. Okay, and as I go further, the dot moves around the path more, but that's not important. So let's put that away. Let's look at the other one. So this dot starts here at the top at 0, 3. And as I move t, this goes the other direction. The first one went counterclockwise. This one goes clockwise, but they mark out the same circle. If I look at them both together, they move toward each other, they pass each other, and then go around the opposite directions to complete the circle. So these two parameterizations mark out the same path, but they go about it in a different way. They both go at the same speed, actually, but in different directions. Okay, so that's basically some of the basics of parameterizations, and just how to create one, how to manipulate one. In the next section, we'll see what we can do with them.